Hello. So we are doing Kirchhoff's voltage law, and we have this exercise here. We have this complex network circuit, so we're going to use Kirchhoff's within the circuit and do some calculations, and then later we are going to do practical measurements for the same exercise, and then we are going to do some simulation as well. So for our calculations, if we have this circuit, we are going to choose our loops. So within this circuit, we have this loop over here. We are going to choose a clockwise direction, and for our mesh I1, and then we're going to choose this I2, and then we're going to choose this as our I3. So for this practical, this exercise, an example basically, we are aiming to determine the current and voltages flowing throughout each point. Then if we have this current direction from this point there, we have this direction. Throughout here, we have this direction. And we know that using KCL, we do not have any current that accumulates at any node. Based on our current direction, this exercise will help us determine or use basic Ohm's law. It will help us also use KCL, but also we're going to use Kirchhoff voltage law. So we are going to start with loop 1. So for loop 1, since we have our voltage source over there, so the sum of all the voltage source should equate to that voltage source across all of this. So we're gonna say V1 is equal to, so this current I1 is flowing through here and flowing in between those two. So those two are in series. So we have I1 if there's a voltage across there, the sum of it is that same current multiplied by R1 plus R2. So plus we have this R3 here. But the thing is with R3, there's two currents, mesh currents that are affecting it over here, because we have I1 in this clockwise direction relative to this resistor, and we have I2 that is opposite it. So the voltage across this section, across this resistor R3, is going to be calculated. I'm going to create a bigger bracket for it. That voltage across there is your I1, because I1 is affecting that resistor, I1 multiplied by R3. And then in the opposite directions, because I1 goes into that direction, but I2 flows up in the opposite direction, which is against, which should be a negative I2 multiplied by R3. So now if we put on our known values, we are going to have 7 is equal to I3. So the sum of 3.3 kilo ohms plus 3.9 kilo ohms. Let's just put it as it is. 3.3 K plus 3.9 K plus I1 multiplied by R3, which is 270 minus I2 multiplied by 270. So sum up all the this is I1. Oops, let's grab an eraser. Just want to erase this. This is I1. There we go. So I1 will be this value plus this value. So 270 I1. So if we add 270 plus 330 plus 3.3, I mean, plus 3.9K, it should give us 7470 I1 minus, we'll be left with this, minus 270 I2. All this is equal to 7. So this is our equation for loop 1. All right. And then let's move over to loop 2. Loop 2, there isn't any voltage source that is acting on loop 2. So what we going to do is it's going to equate to Z0. So V for loop 2 is 0. I'm just going to put it like that. So now we still have this current over here, or relative to loop 2. Now, looking at loop 2. Loop 2 is our direction. We have I2 multiplied by R3. If we want the voltage across R3, because I1 is also acting on R3, so we have I2 multiplied by R3. Now we're going to subtract I1 multiplied by R3 because now we are looking or interested in according to loop 2. So I1 multiplied by R3. All of this should give us the voltage of IR3, VR3. Then plus the sum I2 multiplied by R4 for that voltage across R4 plus now also with R5, I3 is also influencing R5 over here. So the voltage across R5 will be I2 multiplied by R5 minus I3 multiplied by R5. I2 multiplied by R5 minus, because according to loop 2, I2 is flowing that direction and I3 is flowing in the opposite direction. I3 multiplied by R5. Okay, now we're going to put everything in order. V is 0 in this case. And then we have I2 multiply R3. What is R3? 270 minus I1 multiplied by R3, 270 plus I2 multiplied by R4, which is 2.2K plus I2 multiplied by R5, which is 1.5K minus I3 multiplied by 1.5K. So we add our like terms. So how many I2s? We're gonna add 270, add 2.2, add 1.3. So for that, we are going to have 3.70 I2. And then for I1, we're gonna have minus 270 minus 270 I1, and then minus 1.5 I3, minus 1 point, let's take an eraser because I was writing I3 already. Minus 1.5 K I3. So this is our formula for, let's go back, I jumped prematurely. This is our formula for loop 2. And then I'm just gonna try to make a separation point here. Right. So for loop 3, we have that voltage source, which is 8 volts. We have, call it V2, which is equal to the sum of I3. See, I3 is influencing R7 and R6. Just going to say I3 sum of R6 plus R7, there's no other currents that are influencing it, plus, if you look at this, there's I2 over there, and there's I3. So we have I3 multiplied by R5 minus I2 multiplied by R5. We are going to put our values. We have 8 over here. I3 R6 is 330 plus R7 is 2.2, 2.2K plus I3 multiplied by R5, 1.5K minus I2 multiplied by R5, which is 1.5K. All right, so 8 volts is equal to, we add all the I3s together. So we're going to add this, we're going to add that. We're going to have 33 minus 1.5K I2. And this is our loop tree equation. So at this point, this is a maths equation, no, a maths problem now, not an engineering equation. So at this point, you can either do your simultaneous equations, or you could do matrices to solve this, because these are three equations. You can do your matrix in this way. Okay. I'll try to arrange these equations, because try to put it in this I1. I'll rearrange these equations in this manner. I3, right, for each loop. So we have our matrix in this manner. According to loop 1, we have 747 as I1, 7470 is I1. What is I2? Negative 270. And our I3, there isn't anything represented for I3, so we're going to put 0. And for loop 2, for I1, we have minus 270. For I2, this is where I'm looking. For I2, we have 3970. 3970. For I3, we have 1.5, so I'll just write the whole thing. 1500. And then for loop 3, what is our I1? It's 0. Loop I2, negative this is where I'm looking. 1.00. The I3 is 430. So loop 1 is equal to 7. Loop 2 is equal to 0. Loop 3 is equal to 8. So once we are able to calculate this, we'll be able to get our I1, I2, I3. That is going to give us our mesh currents. This is only a math problem in this case, as I won't do any calculations on it in this video because it's going to be an even longer process. Basically, we need to find our determinant and first for this matrix now and incorporate voltages on that side. It will be a much longer process, but in any case, I have done the calculations already on the side, which it was going to be a longer video if I had. So I'll just show them now. So for our mesh currents, they would equate into these values over here. I1 would be that 0.917 milliamps, I2 0.95 milliamps, and I3 would be 2.339 milliamps. So to get these currents for the current flowing in each resistor, or you would then use KCL based on this direction. KCL suggests that current flowing through IR2 is given by the current flowing through IR2, that current flows into this section over here, and then this, based on this current over here, it flows towards that direction. So once we are able to determine this current direction, we'll be able to determine the current according to I1, what IR3 is. IR3 is I1 minus I2. So we then get our current in each resistor, and then it's Ohm's law from there. Once we know the current that is flowing there, it would be that current multiplied by R to get the resistor across each resistor, which is given by these voltages over here. So for us to prove these voltages, we would then head to our practical session. I will end this video here and then join in on our next session for the practical. All right. Thank you.